Have you ever stopped to think about the software that runs our world? I mean, really think about it. The code that's flying our planes, managing our power grids, the stuff inside medical devices, this isn't software that can just be pretty good. Nope, it has to be perfect. Today, we're going to pull back the curtain on the incredibly elegant and powerful idea that makes this possible. It's this surprising, beautiful bridge between abstract logic and, you guessed it, computational machines.
Seriously, just think about that question for a second. How can you be 100% certain a flight controller will never, ever enter a catastrophic state, or that a nuclear reactor's safety system will always kick in when it's supposed to? These aren't just some academic thought experiments. These are questions of life and death, and they represent a massive, massive challenge for computer science.
So here's the game plan. First, we're going to define the core challenge, what we're calling the forever problem. Then we'll look at the two key ingredients we need for a solution, a special kind of logic made for time and a unique type of machine built for infinity. And then we'll see how they snap together to create this incredible bridge that really is the foundation for all of modern software verification. Let's get into it. All right, let's dive right in. The first thing you have to get your head around is why these systems are so incredibly tricky to get right. And it's because they're just fundamentally different from, say, an app on your phone that you open and close. See, they're what we call reactive systems. Their entire job is to run forever, 24/7, constantly listening for inputs from sensors, from users, from other computers, and just reacting to them. You can't just run a bunch of tests and call it a day, because the number of possible things that could happen over an infinite lifetime is, well, it's infinite. And that, right there, is the forever problem. So how do you tackle an infinite problem? Well, you can't use plain old English. You need a way to speak with absolute mathematical precision. You need a language that can describe how things behave, not just right now, but across the entire sweep of time. And that language is temporal logic. A guy named Amir Panueli really pioneered this for program verification way back in 1977. And what it does is it gives us a formal grammar to nail down properties over time. So instead of just saying, this is true, we can now say things like, this will always be true, or this will eventually happen. It seems like a simple little add-on, but oh man, is it powerful. And right here, this is where you really see the power. This is how we take a vague promise and make it rock solid. Just look at that first example. In English, we might say, a request is always eventually granted. Okay, sounds good. But in linear temporal logic, or LTL, that becomes a precise mathematical statement. The G stands for globally, or think of it as always. The F stands for finally, or eventually. So the formula says, it is always the case that if a request happens, then it is eventually granted. Zero ambiguity, it's perfect. Okay, so we've got our language. But a language is just a description, right? It's a blueprint. The next piece of our puzzle is the machine, an engine that can actually run and check these infinite behaviors. And this is it. It's called an omega automaton, or an omega automaton. That omega, of course, stands for infinity. Now, unlike the simple automata you might have learned about in school, these things are specifically designed to handle infinite streams of input. The most famous type, the Bucci automaton, has this really fascinating way of saying yes. It doesn't just stop on a final state. Instead, it accepts an infinite sequence only if it visits a special accepting state again, and again, and again, infinitely often. It's literally designed to make sure good behavior doesn't just happen once, but that it keeps happening forever. And this is what makes them the perfect tool for our forever problem. Reactive systems have these endless behaviors, right? And omega automata are designed from the ground up to recognize patterns in exactly those kinds of endless sequences. I mean, it's a perfect match between the problem and the machine. So, let's recap. We have a formal language to describe infinity, and we have a special machine to process infinity. And now this is where the magic happens. This is the groundbreaking idea that connects these two worlds, and honestly forms the cornerstone of all of modern verification. The best way to think about it is like this. That temporal logic formula, it's declarative. It's like a blueprint that describes what a safe system has to look like. The automaton, on the other hand, is operational. It's a machine. It describes how to actually check for a specific sequence of events. So you have abstract logic on one side and a concrete machine on the other. And this crucial insight gives us the automata-theoretic approach, which was pioneered by brilliant computer scientists like Moshe Vardi and Pierre Wolper. The whole process is just stunningly elegant. Step 1, you take a property you want to check and you write it down as a temporal logic formula. Then, and here's the genius move, you can automatically translate that logic formula into an omega automaton that accepts exactly and only the behaviors described by that formula. Which leads us to this beautifully simple summary. A really deep, complex question about logic becomes a simple mechanical question about a machine. For example, if you want to prove a system is safe, you can create an automaton that recognizes all the unsafe behaviors. And if that automaton doesn't accept anything, if its language is empty, you've just proven with mathematical certainty that your system is perfectly safe. You've solved the forever problem. Now, this isn't just some cool theory stuck in a textbook. This bridge between logic and automata has had an absolutely revolutionary impact on our ability to build reliable systems. So let's take a look at the real payoff here. So what does this get us in the real world? Well, it lets us handle complexity on a scale that is almost impossible to wrap your head around. Using techniques built on this very foundation, we can now analyze systems with this many states. That's a 1 with 20 zeros after it. It's more than the number of grains of sand on every single beach on planet Earth. And yet, because of this bridge between logic and machines, we can systematically, automatically, and provably verify systems that are that complex. It's just mind-blowing. This whole approach powers several really critical tasks. The most common one is model checking. Basically, you give it your system and a rule, and it tells you if the rule is ever broken. Then there's satisfiability. This lets you check if your rules even make sense together before you even start building anything. But the real holy grail is synthesis, automatically building a system that is guaranteed to be correct right from that logical blueprint. And the impact is just unbelievably broad. This isn't just for aerospace or power grids. These very same ideas are used to prove that the chip inside your computer is flawless, and even to analyze the complex reactive behavior of biological systems, like gene regulatory networks. So from hardware to living cells, the fundamental logic is the same. So we'll end with this thought. We've seen this profound, deep connection between logic and automata that lets us transform an abstract description of what we want into a concrete machine that can check it for us. It's a truly beautiful idea that turned a seemingly infinite problem into a solvable one. And it really makes you wonder, right? What other impossible problems out there are just waiting for the right bridge to be built?